Hello everyone, welcome to Brain Blitz Audios. Today in this episode of Mind Maps, we'll be dealing with dual nature of radiation and matter. This is the 11th chapter in the grade 12 syllabus for physics in CBSE. And as always, we'll be using the help of this mind map in order to explain the chapter. The chapter is very simple, but it's very important. It's a part of modern physics, and therefore we have chosen this mind map and we're going to explain it in some detail in this video. So, dual nature of radiation and matter. Now this is the most important chapter when it comes to microphysics, because microscopic physics begins here for grade 12. And in microscopic physics we'll be talking about matter, atoms, subatomic particles, etc. So today in this chapter we'll be looking at the dual nature of radiation. We'll be looking at the contribution of scientists towards microscopic physics, some contributions. Then we'll be looking at photoelectric effect and the observations and also the equation for the photoelectric effect. Then in the end we'll be looking at matter waves, the de Broglie's relation, and an experiment that proves the de Broglie's relation. So without further ado, let's look at dual nature of radiation. So in this universe we have two types of things. The universe is composed of radiation and material. Radiation is present if we are looking at general radiation such as light, radio waves, etc. Then all of this radiation occurs in waves. So if we're able to differentiate it out here, radiation versus material. So radiation occurs in waves, while materials are usually they are usually transported in a straight line. So a light wave will travel as a wave, while an electron will be shot in a straight line because it's material. Next, when it comes to radiation, there is no property called mass. So radiation has no mass, while material has mass. Material is what matter is made of. So matter is something that has mass and occupies space. In radiation, there is only presence of energy, while in matter you can actually convert mass to energy and vice versa. So energy is present alongside other properties such as mass, charge, etc. When we're talking about radiation, we can classify radiation in dual natures. That means you can think of both of the light as a radiation, has both wave characters as well as particle natures. So earlier we thought that light was just a ray, then we realized that it's a wave, but after looking at some other properties we think that light also has particle natures. So now we believe in a dual nature of radiation. So radiation such as light has both wave character that describes interference, diffraction, etc., and particle natures that look at photoelectric effect, etc. And properties such as interference can be explained by wave nature, and when light is of sufficiently low wavelength we can say that it behaves like a particle. The wavelength of light is in the order of 10 raised to minus 9 meters. So therefore it's very small enough for it to behave like a particle. Light particles, which we call photons, have definite energy and definite linear momentum, and these particles are called photons. The energy of each photon is found by using the equation E is equal to h nu, where h is the Planck's constant, and nu stands for frequency. In momentum, we divide the energy by the speed of light, so we'll get a value of h by lambda. Now the reason why we get h by lambda is because frequency is equal to c by lambda. So that's what So basically, if speed is equal to distance by time, time is equal to distance by speed, but frequency, which is 1 by time, is equal to speed by distance. So that is what we're looking at here. So now that we've studied the dual nature of radiation, let's look at some contributions with respect to dual nature of radiation. Now, the most important personality here is Albert Einstein. Einstein, after an average academic career, he gave us the quantum theory of light in 1905 alongside Max Planck. And at that time, he was working as a grade 3 technical officer in a patent office. Einstein, he also gave theoretical explanation of the photoelectric effect, which we'll study later in this video. So we'll be looking at photoelectric effect and Einstein's theoretical explanation. And for this, he was awarded the Nobel Prize in Physics in 1920. And this was based on the theories of special relativity, etc. And besides Einstein, there are many other people who have contributed to dual nature, such as Heinrich Hertz and Leonard Hallwalks, etc. They all have contributed in terms of the photoelectric effect. And that is what we'll be studying next, the photoelectric effect. The phenomenon in which electromagnetic radiation of a suitable frequency falls on a metal surface, leading to emission of electrons, is called the photoelectric effect. Now, emission, is basically removal of an electron from the metal surface. So when a light of small sufficient wavelength is incident on a metal surface, electrons are ejected from the metal, and the phenomenon is what we call photoelectric effect. Now, since the light is ejected by photons, so since it is ejected by photons, we call the ejected electrons as photoelectrons. Now, the thing about the photoelectric effect is that it requires a minimum energy equal to work function so that the electron can be removed from the metal. And this work function, it is dependent on the metal. Now, usually we represent it with phi. You can also use omega in order to represent the work function. And the thing about photoelectric effect is that it was discovered by Hertz, Leonard, and Hallwalks. And they discovered it using a very simple setup, which is this one. So this is how Hertz and Leonard, they observed the photoelectric effect. So this is their device that they used. So this setup contains an evacuated glass tube, and this glass tube, it has two electrodes. The cathode is where light is incident on, and it emits the electrons. So the cathode is also known as the emitter. Now, the other electrode, which collects the electrons, is called the collector, and it is the anode in this case. So in order for a cathode to release electrons, it has to be made out of a photosensitive substance. So the cathode has to be photosensitive in order to act as an emitter. And the examples include zinc. Now, in this case, we see that the cathode is the emitter and the anode is the collector. However, we can also change the polarity. We can make this as the anode and this is the cathode, and still it will be the emitter here and the collector there. So we can reverse polarity. Reverse polarity is also possible. Now, in order for electrons to move from the cathode to the anode, we apply an external accelerated potential difference. So apply varying potential difference which is external, across the two electrodes. And when the light is incident through this tube and it hits the cathode, due to the photoelectric effect, the electrons are now emitted from the emitter, and then they move towards the collector. Now, when they reach the collector, they are taken inside, and then you can see the flow of current I through the circuit, and that is measured here in the ammeter. So due to the movement of electrons through the tube, you can actually pass current through it, and this current is called photocurrent. However, this process does not just happen when there is a cathode and an anode. Since the electrons themselves have energy, this phenomena also works when the emitter is an anode and the collector is a cathode. That means when the polarity is reversed, photoelectric effect also takes place. But the emitted electrons, they are usually repelled by the cathode here. The electrons with more energy, they reach the cathode, and then the current is formed. But the current decreases as we reverse the polarity. And as we increase the potential difference in reverse polarity, there will come a time called a potential difference called V0. And in this V0, there is no emission of electrons because the potential difference is too much for the electrons to move across the tube. So when this stage happens, we can say that the work done by the potential difference, that is stopping potential, it is equal to the maximum kinetic energy of an electron. So when we're looking at potential, so since potential V is equal to work done divided by charge, and work done is equal to QV, and here at stopping potential, the charge is the charge of an electron, so we can just write that as E, and the voltage, the potential here is V0 because it's stopping potential, so work can be written as EV0. And according to the condition in the photoelectric effect at stopping potential, EV0 is equal to half m V max squared. So for maximum kinetic energy to occur, you need maximum voltage. So maximum kinetic energy of the electron is equal to the work done by the potential difference. Now, Hertz and Leonard, they have shown us many observations. This is the basic equation they found out when the work done at stopping potential is equal to the maximum kinetic energy. The first observation is that photoelectric current, it increases with increase in the intensity of light. As you can see here, it increases with increase in intensity. The next observation is that photoelectric current, it increases with increasing accelerating potential. So as the potential increases, the current also increases. But it does not increase forever. At a specific point known as saturation current, the photocurrent becomes stable and it stays constant. Now, this is when the potential difference is increased. What happens when you reverse the polarity? When you reverse the polarity, the potential difference, the current starts decreasing, and at a specific point known as V0, you get your stopping potential, where the current is equal to 0. So photoelectric current, it increases with increasing accelerating potential. However, it decreases to 0 at stopping potential. So when you reverse the polarity, you can also decrease the amount of photocurrent. Next, the stopping potential itself is independent of the intensity. So stopping potential and intensity does not have any relation. However, when you have, say, this setup, where the current is passing along with respect to voltage, the potential, then the saturation current, it increases with increase in intensity. So when you have a light of more intensity and a light of less intensity at the same potential difference, then the intensity ensures that the saturation current is more in the case of more intensity, and vice versa. Next observation is that stopping potential increases with the increase in frequency of incident light. So that means for a graph like this, it has the same, for a light of same intensity but different frequencies, the saturation current remains the same, but the stopping potential, it goes more negative, so it increases in the negative direction. And the last observation is that the emission of photoelectrons takes place above a certain frequency, and that frequency is known as the threshold frequency. As you can see here, above a certain lambda naught, you can find the increase in kinetic energy and there is photocurrent possible. However, when your frequency decreases and it's less than threshold frequency, then this is not possible. So there is no emission. So emission happens only when you have an increase of frequency greater than the threshold frequency. So using these observations, we have the laws of photoelectric emission. The first law states that for a given frequency of incident radiation, the number of photoelectrons emitted is directly proportional to the intensity of incident radiation. The kinetic energy of photoelectrons is directly proportional to the frequency of incident radiation, but it is independent of intensity of radiation. Photoelectric effect does not occur if the frequency is below the threshold frequency, and photoelectric effect is an instantaneous phenomenon. So these are all the laws that we get by physical examination. Now the problem is that by using the wave theory of light, the photoelectric effect does not occur, because as per wave theory, maximum kinetic energy is proportional to the intensity, but experiments show that the maximum kinetic energy is independent of the intensity. As per the wave theory, sufficient intensity of radiation enables ejection, but below threshold frequency, there is no photoelectric emission. And with respect to the wave theory, the statement is that a time delay between exposure and ejection occurs, but in experiments, we find that photoelectric emission is an instantaneous process. So this is where the wave theory goes wrong. So Einstein, he decided to use the particle nature of light here. According to Einstein, light consists of particles associated with definite amount of energy. These particles are the photons, and they have energy packets called quanta. And the possession of energy now enables Einstein and the scientists in order to explain the photoelectric equation, and this was done theoretically. So according to Einstein's photoelectric equation, the emission of a photoelectron was the result of interaction of a single photon with an electron in which photon is completely absorbed. So that means the energy is absorbed and then the electron gets released. And then what happens is that the minimum amount of energy required to eject an electron is called the work function. Phi, the work function, is defined as the minimum amount of energy required to eject an electron. And when a photon of energy h nu is absorbed by a metal surface, and it's absorbed by an electron, and when this energy is equal to phi, then what happens is that we get the maximum kinetic energy of the electron as E minus phi. So maximum kinetic energy, which we can represent as EV naught, is also the difference between the total energies supplied to the electron minus the work function. This we can write it as h times nu minus nu naught, because the work function phi can be written as h nu naught. So therefore we can write the kinetic energy as hc by lambda, that is energy, minus phi, that is work function. Now lambda naught is hc by phi, and this is also the threshold wavelength, and so therefore mu naught is threshold frequency, and therefore you can find k max as h times nu minus nu naught. This is essentially the equation of Einstein. Einstein's photoelectric equation is that the maximum kinetic energy is the difference between the frequencies and Planck's constant. So this is the equation. Now if lambda is lambda naught, then so if the lambda that is if the wavelength that is supplied to the surface is suppose lambda naught, that means it's just equal to the threshold wavelength, and the frequency is just equal to the threshold frequency, then accordingly we can say that kinetic energy, the maximum kinetic energy of an electron, is 0. So what does that mean? That means the electron may just come out. So that if in a normal scenario, if there was more energy, then the electron gets emitted outside. If it was equal to lambda naught, then it only just comes out. There is no energy inside it to propel it further outside. So since the frequency is inversely proportional to wavelength, as the wavelength increases, the frequency decreases, and therefore energy decreases, so no electron comes out. If there is lesser wavelength, the less wavelength implies more frequency implies more energy, and therefore photoelectric effect takes place. And the threshold wavelength and threshold frequency, these are both dependent on the metal used. So if the metal needs less frequency, then you can emit electrons more, otherwise you can't emit a lot of electrons. So now we've studied about the dual nature of radiation and the photoelectric effect. Let's look at what are matter waves. So we've talked about radiation, now let's talk about matter. Matter also can be expressed in the form of waves, and these are called as matter waves. All matter can exhibit wave-like behavior. For example, if you have a beam of electrons and you put in a slit in between them, then you find that the electrons diffract. So therefore there is some wave nature in matter as well, besides the particle nature. And this wave nature is given to you by de Broglie's relation. So in de Broglie's relation, consider an electron of mass m and charge e. It is accelerated through a potential difference v. If E is the energy acquired by the particle, then the energy is equal to E times V. I mean charge times V, potential difference. And this energy we can represent it as half mv squared. Here the small v represents velocity. So velocity square is 2e by m. Velocity is equal to 2e by m the whole root. Now, de Broglie's relation is given as wavelength is equal to Planck's constant divided by the momentum. So lambda is equal to h by p. H by p can be written as h by mv. Here v, which stands for velocity, can be written as 2e divided by m root. And since we can put this inside, when you put this inside the root, it becomes m squared. M squared divided by m is equal to m. So therefore lambda becomes h divided by 2me. Now the energy here, we can write it as 2m times electron volt. electron volt. So H divided by root of 2 MeV is equal to the wavelength of the matter wave. So lambda here stands for wavelength associated with the particle, which is also known as the de Broglie's wavelength. And when you have V is equal to stopping potential, then you'll get EV as K max. So this formula here is the situation when the voltage is equal to V naught. Now, this was all theoretical. We need practical proof in order to prove these theories. So, what happened? In order to prove the de Broglie's relation, Davison and Germer, they decided to conduct an experiment. So, you can see that a beam of electrons were emitted by an electron gun, and it is made to fall on a nickel crystal cut along the cubical axis, and it is cut at now this electron beam is at a particular angle. Now the electrons are reflected at a particular angle, say theta, and then the scattered beam is received by the movable detector. So after doing this experiment, we found out that the lambda here was equal to de Broglie's wavelength. And H by P, we can also write it as 1227 divided by root V nanometers. And when V is equal to 54 volts, we got a value of 1.67 angstroms. So therefore, we've proved the wave nature by using Davison-Germer experiment. So this experiment verifies the wave nature for electrons and the relation with de Broglie's wavelength. So we proved the relation correctly by using the Davison-Germer experiment. So that concludes the chapter Dual Nature of Radiation and Matter. We hope you found this mind map interesting. For more of our mind maps, don't forget to click the link in the description down below. That leads on to the playlist, which gives you more mind maps. For more of our useful and interesting content, don't forget to subscribe to our channel, which is Brain Blitz Audios. So until the next webisode, take care, stay safe, bye-bye for now.